Okay, so I'm going to show you a third method for solving this recurrence relation. What you can do is you can consider the similar differential equation, which looks like this: ay double prime plus by prime plus cy is equal to 0. And the idea is, if you know how to solve this one, you will be able to get from there back to here. If you can solve this one, you can solve this one. So what I'm going to do here is, first step is I'm going to differentiate both sides. And since this is I'm considering y as a function of t, since this is a linear differential equation, and since differentiation is a linear operation, what happens here is if you differentiate both sides, you have y triple prime plus by double prime plus cy prime is equal to, derivative of 0 is just 0. So you can repeat that process and nothing crazy happens. If you do that n times, then you'll have the n plus 2 derivative here, you'll have the n plus 1 derivative here, and you have the nth derivative here. The nth derivative of 0 is 0. And just to remind you, these are functions of t, so I'll just write that right here, just because the notation gets a little confusing. And so then from here the idea is you just evaluate at your favorite point. Mine is 0, so I'll just plug in t is equal to 0 to this equation, and then you just have this. And so then what you can do is you can define a recurrence relation. So we're forgetting about this, and we're just starting here. So if I now I can define f of n. If I let f of n be the nth derivative of y evaluated at 0, then what I get from this statement is I get the recurrence relation as like this would imply that I have this recurrence relation that a fn plus 2 plus b fn plus 1 plus c fn is equal to 0. So then all I have to do if I want to solve for fn is I just find the nth derivative of y, and I evaluate it at 0. And so we know how to solve for y, since solving for y is just solving this differential equation. And so if you do that, you'll see that y is equal to a constant times e to the first characteristic equation root, and another constant times the second one. And so here I'm assuming that the characteristic equation doesn't have a repeated root. If it did, we'd have to consider that separately. And this is the same case that I've neglected to address in the other two methods that I've shown so far for solving this thing, but I'm going to show those in a separate video rather than show that separate case in every single different derivation of this thing. And so then the idea from here is you can take this, differentiate it n times. You're going to have the chain rule here. The first time you differentiate, you'll have c1 times lambda 1 e to the lambda 1 t. And if you do that n times, you're just going to get n copies of this first lambda value here. And same with this one over here. And then it's just evaluating this thing at 0. So this will be, when I evaluate this at 0, that will be f of n. So this is just going to be c1 lambda 1 to the n. Then if I put in 0 here, this is just 1. Over here, this is c2 lambda 2, oops, this is to the n. And that's your solution. So this is probably the easiest way to to figure out the solution to this recurrence relation, I would say, but it kind of relies on the fact that you know how to solve this differential equation. But it's pretty cool that you can get from the differential equation back to the recurrence relation.